Welcome to Empowered Learning. This is the first video in the video series on power series. Before we get started covering power series, I want to make sure that anyone that is watching this video is familiar with the following topics: sequences, series, the integral test, the comparison test, meaning the direct comparison test and the limit comparison test for series, the alternating series test, the ratio and root test. So if none of those, or if at least one of those topics does not sound familiar to you, I suggest that you go back and watch the videos that I have on these topics first. Okay? If you are familiar with all of those topics, then you are at a point now to where we can actually talk about the power series. So we see that the power series is just an infinite series, but it's special. Okay? And so it's special because it has this variable x in it as well as variable n in it. And so up until this point, if you are in a second year calculus course, if you've been watching my videos on the topics I just aforementioned, then you'll know that we've been dealing with series, and most of our series have been defined in terms of some variable n, which is a subset of the natural numbers. What we're now doing is adding x to these particular series, where x can be any real number. And when I say any real number, it depends upon what the series is and how that series converges as to what any real number set that would actually be. Okay, so let's go ahead and see what a power series actually is. So a power series is a series that looks like this. Okay, so we have the sigma notation or summation notation. Instead of starting at n equals 0, like how we did for a geometric series, we will start at n equals 1, like how we do for a geometric series, we will start at n equals 0. And this c sub n's here are just going to be the coefficients for our basically polynomial that this turns out to be here. And of course, this x in this case will be allowed to be, for all simplistic purposes here, any real number. Okay. And so we'll kind of narrow down on that as we get deeper into this topic here. Now, we see that a more general form of the power series, because this is a specific type of form of it, but the most general form for it here will look like this, where instead of just having x right here, we have an x minus a, where this a is some real number that our power series is said to be centered about. Okay, and we'll see later on what that actually means. Now, in the grand scheme of things, there's not much difference in between what we see here and what we see here, except for the fact that everywhere where we see x up here, it's replaced with x minus a down here. Okay, so not much there. Now, let's talk about what all these parameters mean, though. So the c sub n's, again, are just our real number constants or coefficients. The x that we see here is what's considered the variable of the power series. The a is the number that defines where the power series is centered about, as I said earlier. And n here is going to serve as our counter to let us know, well, how many terms we need to go out to be able to figure out what the power series is going to be, or how long it's going to be, or how accurate it's going to be. Okay, and of course, in general, though, this n is being used to increase the exponent in each of the term of the series as we listed out. So like here we have really x minus a to the 0, x minus a to the 1, x minus a to the 2, x minus a to the 3, and this is the n equals 0 term. This is the n equals 1 term. This is the n equals 2 term, so on and so forth. So you see how what the n actually is in terms of the exponent that's on the x minus a here. Okay, so that's essentially its function in this power series. So now that we see in general what a power series looks like, let's talk about some of its basic characteristics. So first, we know that a power series is just a compact way of expressing a family of regular infinite series. Okay, I'll say that again. It's just a compact way of expressing a family of regular infinite series. Each valid value for x reveals one of the separate series within this family of series that we have. And I have an example here just to kind of make my point. So suppose that we are considering this power series here. Of course, sigma with n equals 0 going to infinity. And of course, on the inside, we have 2n plus 1 times x raised to the n. So all that's on the inside of the sigma or summation notation here. Okay. So with that being in mind here, if we were to list out all the terms that we see there, then of course, you see we've listed it out here. So when n is equal to 0, of course, this first term would just end up being 1. When n is equal to 1, of course, we'll put a 1 here, and we have 2 times 1 is 2, plus 1 is 3, and x raised to 1 is just x, so that's why we get 3x in the second term. And then, we go so on and so forth by letting n equal 2, 3, 4, 5, 6, whatever. Okay. So if we look at it this way, we know that here, that this in general is going to be what this power series is going to look like if we list it out term by term. Okay. If we were to let x equal 1 and let x equal 2, and let's assume that these are valid values for this power series, then we could produce 2 regular infinite series from these x values. So for instance, if we took this same power series and let's say we just let x equal 1 here, okay? Well, this is what it would look like. And when we list out everything, what we see here is that we end up having a series, which is just the sum of a sequence of numbers. And of course, if x is 1, then what we essentially get here is the list of numbers that are odd, starting at 1, going 1, 3, 5, 7, and we're just trying to add them up. Okay. And of course, anytime we take a sequence of numbers and we add up all the numbers in that sequence, what we have is a series. So technically, if x is equal to 1, this result here actually just ends up being a separate infinite series. Okay. So if x is equal to 2, then instead of putting a 1 right here, we'll put a 2. And this is what this will look like. And so at that point, what we have is another list of numbers that comes out that we're adding up. And of course, this would be the other single infinite series that comes out of this family of power series. Okay. So again, the point that I'm making here is that if we keep the power series just in general here, like how you see here, with us just having a general x and a general n there and nothing's been plugged in for x, we have a power series. When we identify a specific value for x, then what we do is identify a single member or a single infinite series out of that family of series. And of course, we give the name family of series power series. So that's why it's called that. All right, so the characteristic number 2 that we want to talk about is that in a power series, n is going to be treated as a counter, as we mentioned before, while x is treated as a variable. And when we set x to a single number, say x equals 2, like how we saw earlier, the power series reveals one regular infinite series, just like I mentioned before. The variable for this regular infinite series is going to be n. So once we actually plug in a value for x into the power series, it extracts out a single infinite series. And for the infinite series, its variable is going to be a subset of the natural numbers, which is what n is. All right, so the third characteristic, and this is probably one of the more important ones here, the domain of the power series is a set of all x values that yield members of the power series family that are convergent. Okay, so what that means is remember, domain means x values that are quote unquote valid. Okay, in terms of functions, what that meant was we have an x value, we plug it into a function, x value that's a real number, we plug it into a function, we get out a real number. Okay. In terms of power series, domain is x value that we plug into the power series, and it yields for us an infinite series that actually converges, meaning that if we add up all the numbers in that separate series, whenever we plug in a particular x value that's in the domain, it will add up to be approaching some number. Okay. And so, again, what is important for us for the power series are the specific members of the family in the power series that actually end up being convergent infinite series. Okay. So we're going to give a few examples here. So let's consider this power series here, where we have a sigma notation, n is equal to 1 to infinity, and inside the summation operator, we have x minus 5 raised to the n, all that divided by n. So if we let x equal 4.5, so that means we plug in 4.5 right here, we see that we end up getting inside the summation operator a negative 1/2 raised to the n divided by n. And if we kind of go through all the hoops to see does this particular series converge or not, we see that it converges conditionally by the alternating series test. Okay, and so it will be easy to show that if we took the non-negative portion of what our sequence is here, and we were to show, and we would be able to show rather that the b sub n terms, as n increases, the value of the b sub n terms would decrease. That would be easy to show. And we would also have to be able to show that the limit of the b sub n would be going towards 0 as n approaches infinity. So all that is relatively easy to show. So by alternating series tests, we know that this particular power series, when x is equal to 4/5, or put another way, this particular infinite series is going to converge, okay, conditionally. Now, when x is equal to 2, that means we would come here and plug in a 2 right here. This is the power series that we would get. We get summation of -3 raised to the n divided by n. And we see for this one that this particular series here will diverge by the nth term test for divergence. Okay, and so simply put, we know that this particular limit here would not equal a real number. Okay, to be specific about it, if I wanted to kind of get formal here, I could take this negative here and move it out to be a -1 raised to the n, and kind of think of this as just +3 raised to the n. If we just took the limit of this part, we have the exponential function, or exponential sequence, I should say, 3 raised to the n, and we have the sequence n. If we thought of this as like 3 raised to the x over x, then, and if we took the limit of this as, let's say, x approaches infinity, it's simple to know that the exponential function 3 raised to the x goes to infinity as x goes to infinity, and x does too, but this 3 raised to the x function grows faster than this one, okay? So because of that, this would be actually approaching infinity here. And what you would actually end up having here, if we looked at this limit in this case, is we would have a plus or minus infinity. And of course, since it's plus or minus, it's not going in one direction in particular. So that is why I put here does not exist. Okay. Of course, if it was positive infinity or negative infinity on its own, it would still be does not exist anyway. So doesn't really matter what you want to call it. At the end of the day, we know that the limit doesn't exist. Okay. So we see an instance where when we plug in an x value into a power series and it extracts out an infinite series that converges. And we've seen an example to where when we plug it in, the corresponding infinite series that is extracted as a result diverges. Okay. All right. So for the last and final characteristic that we want to talk about right now is we know that the x values are not in the domain of the power series produce divergent series as shown. So here just reiterating the fact that if your x values that you plug into the power series, if they don't produce convergent infinite series, then that means that the x values aren't in the domain and thus they're producing divergent series. Okay. All right, so now that we know that, we want to know, so what will I be asked to do with power series? Okay, so when dealing with power series, you'll be asked to find at least one of the following properties of a given power series. First, for what values of x does the power series converge? In other words, we want to find the domain of the power series or the valid values of x that will produce infinite series that converge. Okay, so that's one of the main things that we would want to know about a power series. Now, the next thing is what is going to be the radius of convergence of that given power series. If we have our power series centered about some value x equals a here, then we want to know, all right, well, how far can we go to the right and how far can we go to the left to be able to find x values that when we plug them into our power series, we will end up getting a corresponding infinite series that converge. Okay. So what you see here going to the left or to the right, this distance from A to wherever we stop, that is what we're going to call R, which would be our radius of convergence. And we'll also call this ROC. Okay, but we'll call it R for short here. So the interval of convergence is this actual interval that I'm drawing here. I'm going out this far to that far. Okay, so it's just the interval of x values where that happens. The radius of convergence is just the distance from A in either direction you go to find those values. Okay, so what is the radius of convergence and interval of convergence exactly? And I put that question there, but what this really means is, all right, well, how can I actually identify it based upon the type of power series that I have? And we actually have a theorem called the ROC/IOC theorem, or radius of convergence / interval of convergence theorem. That's what I call it, at least. You can also call this the good side of the family theorem. Of course, I made that up too. Because of the fact that what we're really trying to find out is, out of all the x values that we could possibly have or plug into a power series, we only want the ones that converge, or that make the power series converge. Or we only want the x values that we plug into the power series that extract out infinite series that make where those infinite series actually converge. In other words, we want the quote unquote good x values, not the quote unquote bad x values. Good x values make the infinite series that come out converge. Bad x values make the infinite series that result out diverge. And so that's why I call it the good side of the family theorem, because we're looking for the x values that are going to be good to us, and of course, good to us in this case is we have a power series that produces an infinite series as one of its members, and that particular infinite series converges, okay? All right, so let's look at this particular theorem here. So for a given power series that looks like what we've seen before here, one of the three cases that I'm going to state below will always be true for a power series, okay? So case number one, I call this the single member family. A power series yields only one convergent series, meaning that we only have one x value that we can plug into the power series that will result in an infinite series that converges, okay? And so, of course, that's the smallest one out of all the cases as far as the number of x values that will be able to be used to produce convergent infinite series, okay? Now, case number two is a large size family. And so we have a power series that yields infinitely many convergent series. And normally this case is when we can plug in any x value that we want into the power series, and the resulting infinite series will always converge, okay? So this is like the largest size family you can think of. Now, more than likely what happens is the case three situation, which is we have what I like to call an average size family, but we know that there's going to be some x values we're going to include, some we're going to exclude, okay? So there exists at least one positive number r, and remember this r stands for radius of convergence, okay, such that the power series yields a set of convergent series if the absolute value of x minus a is less than r. That's just a fancy way of saying here, if we have our interval centered at a, we can go out in this direction, r units, go out in this direction, r units, okay? And so here, this would be like a minus r. Here, this would be a plus r. And of course, we're looking at this in terms of x values. So that is essentially all that means. So looking at a, if we go out a distance of r in either direction, then here, all those x values there will produce infinite series that converge, and anything outside of that interval there will produce an infinite series that diverges. So hence here, absolute value of x minus a is greater than r. That's all this stuff that's out here and out here. Whereas everything that we do want is going to be inside of here, okay? So all this business here. And so for any power series that we deal with, the interval of x values that we have that's going to produce infinite series that converge is going to be one of these three cases, always. And so, of course, our job is once we know what kind of power series that we're dealing with, we want to be able to find those x values that are actually going to produce convergent infinite series. All right, so again, we want to note that r is the same as radius of convergence. And note too, again, just this absolute value of x minus a is less than r just basically means we're looking at values of x in between a minus r and a plus r. We call that the interval of convergence. Now, note number 3 is something that we haven't talked about yet, but is important, okay? By default, we assume that our interval of convergence whenever we deal with a power series is going to be something like this, okay? Especially if we have a case 3 situation here, okay? If we have a case 3 situation, then what is undetermined is whether if we plug in a minus r as an x value into our power series, or a plus r as an x value into our power series, it's undetermined whether our power series will produce an infinite series that will converge at those end values. Okay, and so that's what note number 3 is talking about here. It says the endpoint values of the interval of convergence can either diverge or converge, and we must test each endpoint value for convergence in the power series separately. Okay, and so what that means here is that by default, we're going to have this option here. But once we test it, notice that we may still end up with this option, which means that at a minus r and at a plus r, the corresponding infinite series that results is going to diverge in both cases. Or we may have a situation where, let's say the a plus r, whenever we plug that into the power series, it converges, but the a minus r diverges, and vice versa. The a minus r gets plugged in, resulting infinite series converges, but the a plus r, when we plug that in, corresponding infinite series diverges. And we could also have the case where both a minus r and a plus r, whenever they're plugged in, they both produce infinite series that converge. Okay, so the main point here is that after we find out what our radius of convergence and interval of convergence is, we need to use that information to see what are going to be the end values of our interval of convergence and test those to see whether we have convergence properties at the end of the interval of convergence or not. Okay. So now that we see that, the steps that we need to go by in order to take a power series, figure out whether it's going to converge or not, and for what x values that's going to happen, and then, of course, test the end values of that, we do the following. So step 1, we want to use as a first line of defense the ratio or root test to find the radius of convergence for a given power series. Okay. Now, using the radius of convergence, we could find what I'm calling the interval of convergence prime, or IOC prime. And IOC prime is always by default just a minus r, a plus r. It's the open interval of x values from a minus r to a plus r. And remember, a is the number that the power series is centered about, and r is going to be our radius of convergence, how far we go out in either direction of x equals a. Now, if our ROC is equal to 0, meaning our radius of convergence, then of course our IOC prime is just going to be one number. Okay, so it's just a set with one number in. If our ROC is infinite, then our IOC prime is just going to be all real numbers. Okay, now what I was talking about here as being the default, that happens in the case 3 situation, where if our ROC is equal to r, which is going to be some distance in between x value and a here, then of course, if absolute value of x minus a is less than r is the interval, then of course that's going to be where the power series converges, and this absolute value of x minus a greater than r, that's where it's going to diverge. And again, if we go back to here, all that means is what I was talking about right here, where it's real dark here, diverges, inside here, converges. And again, we gotta see at the end values whether it's going to converge or diverge there. And that is what, if we keep going here, that is what step 3 is about. We want to test to see if the given power series converges or diverges at those end values there. Okay. So the given power series might converge or diverge here. IOC will be equal to IOC prime plus any convergent endpoint that we have. And again, the 4 possibilities that we'll have are listed here. Okay. Now, we realize that we would probably need to employ another test if the ratio or root test produces inconclusive results. Okay, and if you remember, Basically what that means, and I'll just quote the ratio test here. If we have a situation where the limit of absolute value of a sub n plus 1 divided by a sub n is 1, then that means that the ratio test is going to be inconclusive, and thus we're going to have to find another way or another test to be able to show convergence or not. Now, also remember that if this doesn't work for your series that you're dealing with, then what that's probably telling you is that your particular series that you're trying to figure out whether it converges or not is not going to be absolutely convergent. Okay, it will probably be conditionally convergent via some other test, but it won't be absolutely convergent. All right, and so of course here, this is just another graphic of what I was talking about. The convergence interval, which is going to be absolute value of x minus a is less than r, is basically going to be everything that is in here. Of course, everything, all the x values for where it produces infinite series that are divergent on the outside. And then right here where I have these holes, we actually have to test an a minus r and a plus r to see whether the corresponding infinite series will converge or not. All right, so for our first example here, we want to find the radius of convergence and interval of convergence for the given power series. So we're going to follow those steps that I just got through reading here. So the first thing that we want to do, as soon as we recognize what our power series is in its compact form, which is what you're seeing here, we want to go ahead and apply the ratio or root test. And in this instance, it looks like the ratio test would be one that makes a little bit more sense to do here. Okay. Now, if we had something like, let's say, n, we'll say 2 plus n divided by 3n, and all that was raised to the n, then we would probably want to do the root test at that point. Okay. Of course, the root test will help us get rid of this power of n right here. But since we don't have that going on, being that the sequence itself is not raised to some power of n, the ratio test looks good. So that's why we're doing that. So again, for the ratio test, we're essentially trying to figure out what this particular limit is going to be. And what we're looking for here is some value L, and we want that value L to be less than 1. Because if we can have something here, in this case, it's not going to necessarily represent a value. It's going to end up being an expression, but we want to force that expression that L is going to be here to be less than 1. Okay. And so whatever turns out being here, if we can force it to be less than 1, then that will give us the conditions for picking X values that will actually produce convergent infinite series. Okay. All right. So here we know what our a sub n is. It's just what the actual expression inside of our summation here is on its own. And of course, a sub n plus 1, everywhere where we see n, we just replace it with n plus 1. And then we just do absolute value of a sub n plus 1 over a sub n. So you see, I'll just plug everything in. And then there's a bunch of simplification going on here. And then we eventually get to the point where, of course, we have this square root of 1 plus 1 over n, which came from this. And we know that these x raised to the n's reduced to 1, so all we have left is x there. And using absolute value properties, we could rewrite the product of two expressions in absolute value as absolute value of each one separately. Okay. So at this point, we can evaluate the limit, which is going to be evaluating the limit of the product of these two functions here, which means that we can evaluate the limit of each one separately. Okay. Now, notice that for this first one here, we can actually evaluate the limit because the variable that the limit operator is written with respect to is n. So you notice here I plug in the infinity. Of course, that goes to 0. And here we end up having 1 as a result. However, we see that for the limit operator, for the second function here, we have an x. And so since the variable of the limit operator is n, that means to this limit operator, this absolute value of x looks like a constant. And the limit of any constant is just that constant. So that's why we just have absolute value of x here. Okay. So absolute value of x times 1 is just absolute value of x. And remember how we said that whatever ends up here has to be less than 1. So the power series that will end up converging will be the ones where absolute value of x is less than 1. Or put another way, the values of x that are strictly in between -1 and 1. Okay, so this is our case 3 by default situation for the power series. Okay, and so from that, if we go back up here, you'll notice, probably didn't notice this now, but we're going to go ahead and say it now. Notice that this power series just had x raised to the n. Remember, in general, our power series looks like this. So in order for x minus a raised to the n to be equal to x raised to the n, a had to be 0, meaning that this particular power series is centered about the x value a, which is 0 in this case. Okay, so because of that, that's why this interval of convergence here is in between -1 to 1, because of course, if we are centered at 0 here and this represents r, then we can go 1 unit out this way and we can go 1 unit out the other way. And thus we have our x values that are strictly in between -1 and 1. Okay, so what we need to do now, now that we know what the ROC is and what our IOC prime is, we need to test at -1 and at 1 to see if the corresponding infinite series that comes out as a result of plugging in those numbers, will they actually end up converging or not. Okay, so if I go ahead and plug in a -1 in for x, then I'm going to get this result here, and that's what's going to be inside my summation here, because the actual series would be summation of square root of n times -1 raised to the n. Okay, and of course this will be from n equals 0 in this case to infinity. Okay, and so what we are concerned about here is for this particular series, what we're basically doing is testing to see whether the series is going to be convergent or not, and we can do that by figuring out what the how the sequence that makes up that series acts. And so in this particular situation here, we have a square root of n times -1 raised to the n. So that -1 raised to the n has just got a bunch of going back and forth like this. But the square root of n, if we looked at it in terms of square root of x, it looks something like this. So the actual sequence is actually doing something more like this. And it's just getting bigger and bigger and bigger the more we go back and forth. So this is why in general here, this will end up being divergent, because it just keeps on getting bigger and bigger. Okay. Simply put, we know that the limit of our sequence does not exist. And really, the nth term test for divergence tells us that unless we get our limit of the sequence that makes up our series going to 0, we know that the corresponding series is going to diverge anyway. Okay, and of course, if we plug in a +1 here, we see that we end up with the same thing. Okay, so here 1 raised to the n, at the end of the day, this is just going to be 1. I put 1 to the infinity here, but it'll still just be 1 anyway. But this square root of n here, as n gets larger, square root of n gets larger. So that's just going to be divergent as well. So what we have here for IOC prime is actually going to be our true interval of convergence here. So we say here that IOC is equal to IOC prime. So the x values that we can choose for this power series that will produce convergent infinite series will only work if you choose values in between -1 and 1. Okay. All right. So for our next example here, you see that we have a situation where the sequence that makes up this series here, or the sequence that is the foundation for this series, can be looked at as product of two functions here raised to the power of n. And so in this case, the root test is appropriate because we want to essentially get rid of that particular power raised to the n in trying to test for convergence, because it's going to just make it easier for us to do. So in this sense, we essentially need to figure out what is going to be the limit as n approaches infinity of the nth root of absolute value of the sequence that makes up our series here. So we've done some rewriting here. We realize that a sub n is just n times x, all that raised to the n. So therefore, if we do the absolute value of that, we're just going to end up having absolute value of n x. And so again here, if we evaluate this limit, remember that x looks like a constant to the limit. So that's why that goes on the outside here. And if we evaluate the limit of absolute value of n as n goes to infinity, we know that the only way that that's going to actually produce a value that's going to be less than 1 would be in a specific case if we allow this x inside of the absolute value signs here to be 0, because it wouldn't matter what this is at that point. This constant times whatever this is will essentially just give us 0 here. Okay. And of course, it's a little bit more involved than that, because what we'll actually have is this case here. And what I would end up having to do is rewrite this per first year calculus, where I would have to do something like, let's say if I had nx absolute value, I would have to rewrite, let's say this portion here as, let's say, absolute value of x over 1 over n. And this would, if I took the limit of this, this would put me in a situation where I would end up having some number here. And of course, I plugged in infinity here, some number over 0, which would technically be undefined, but we would use L'Hopital's rule at this point, deal with this. And when we evaluate the limit after doing all that, it'll eventually be going to 0. Okay, so I didn't want to get into all the details on that. Simply put, we can see that no matter what this limit of natural log of n, limit of absolute value of n is doing, it doesn't really matter what's going on there. The fact that once all that's done, it's being multiplied times this 0 here, and we're forcing it to be 0 because we're saying the only time that this would actually work is when x is equal to 0. That's what's kind of forcing it to be there. Okay. So the whole point here is that there's only one x value for where this situation here is actually going to be true. Okay. And so this is a situation where our ROC ends up being 0, which means our IOC prime is going to be 0 as well. And the only x value that we can use to be able to produce a series, an infinite series that will converge, would be when we have x is equal to 0 here. Okay. And essentially, that would be, the series with 0. Okay. So that would be the only time that would work. All right. So for our next example here, we notice that we have summation from n equals 1 to infinity of 10 raised to the n times x raised to the n, all that divided by n cubed. And again, this looks like a situation since we don't have n raised to the n as well. We want to use the ratio test to try to find out when this particular series will be absolutely convergent. So we list what our a sub n is, which is essentially what the sequence is, that is the foundation for the series is. And then we do the a sub n plus 1. Everywhere where we see n here, we replace it with n plus 1. And then we just divide. So we just take this, which is written here, and we're going to divide it by a sub n, which is just like saying we're going to multiply by the reciprocal of this. And so that's what's being done here. And then from all that, you can see that there's a lot of simplification going on. And eventually we get to the point after all the simplification is done where we have absolute value of 10x times absolute value of 1 over 1 plus 1 over n. Okay. And so when we take the limit of that, we're going to take the limit of this function and this function separately. Again, since we have an x here and the limit operator's variable is n, this looks like a constant, so this gets factored out. And we just evaluate the limit of this 1 divided by 1 plus 1 over n, all that absolute value cubed. And we see here we can just plug in an infinity for n, and all this just ends up just being 1 at the end of the day, okay, which is what we see here. So 1 times absolute value of 10x is just absolute value of 10x. So we see here that we know that this series is going to converge. If I was to rewrite this, this would basically be 10 times absolute value of x is less than 1. And if I was to divide both sides by 10, I would have absolute value of x is less than 1/10, which put another way, it's just going to say here that my x values are in between a negative 1/10 and a positive 1/10. Okay. I took that a different way here. I just literally translated this as being absolute value of 10x is going to be in between negative 1 to 1, but we see that we end up with the same thing here. Okay. So our ILC prime is all the values in between negative 1/10 and 1/10, and our ROC is going to be 1/10. And so again, the reason that we know this is because if we go back to our problem, notice that a power series in general should be x minus a, should have an x minus a in it. But notice that here we have x raised to the n. So we know from that it's assumed that a is going to be 0. Okay. All right. So from that, we now need to test for the convergence of these of the power series at these two values, at positive and negative 1/10. All right, so if we let x equal to a negative 1/10, then we see here in place of x, we have negative 1/10 there. And if we do some simplification, we see that we just end up having a negative 1 raised to the n over n cubed, being the thing that we need to take the limit of here. And again, we are jumping to just figure out what the limit is going to be, because we know if the limit of the sequence goes to 0, then there is a possibility for the series to converge, okay? But if the limit of the sequence that makes up the series does anything but go to 0, we know automatically that that particular series is going to diverge. And that's essentially what the nth term test for divergence is, okay? So we come here, we have this limit, and we see here that the corresponding series that will come out as a result of this is going to be this series here. And we know this is going to be an alternating P series, okay? So here, instead of trying to do the whole, the nth term test for divergence, instead of trying to do that, we can just jump here to the alternating series test, okay? Because it is an alternating series, so we can use the test that's made for alternating series on an alternating series. So we look at the non-negative portion of what this is here, which is just 1 over n cubed. Of course, if we list these values here, we see that 1 is greater than 1/8, and 1/8 is greater than 1 over 27. 1 over 27 is greater than 1 over 64. So it meets the first condition of the alternating series test. The second condition is that here, the limit of our b sub n, I'll put a sub n here, but it really should be absolute value of a sub n, which is just going to be 1 over n cubed. That goes to 0. So, and this is the second criterion for us that we have to meet for the alternating series test to say that our series converges. So we see here that since our b sub n plus 1 is less than or equal to b sub n, and we see here that our limit as the non-negative version of our sequence that makes up the series that we were talking about goes to 0, it follows that our series is going to be convergent, okay? And I'm going to throw in here that it is conditionally convergent because of the fact that it's an alternating series here, okay? All right, so when x is equal to positive 1/10, we go and plug in everything, and here we end up with just the limit of 1 over n cubed. And of course, the corresponding series for that is this, which is a p series when p is equal to 3. And since p is greater than 1, we automatically know that p series where p is greater than 1 converges, okay? So we see that we will actually have a convergent infinite series that will come out as a result of plugging in x is equal to positive 1/10 as well. So that means that our true ILC here is actually going to be all values of x that are in between negative 1/10 and positive 1/10, including the end values, okay? All right. So let's look at our last example here for this video. And of course, I'm going to do another one to kind of carry this conversation on, but this will be the last example that I do for part 1. We want to suppose that we have some power series that looks like this. And the only information that we have about it is that this power series is going to converge at x equals -4, and we know that it diverges when x is equal to 6, okay? So based upon that, does it follow that the following series converge or diverge, okay? So first we want to look at, well, what is going to be this series here, which is just going to be the series of coefficients here. And again, we don't know much about about what these coefficients are, okay? We know nothing at all, okay? So in looking at this, from the info given, we can deduce that our given series is going to be convergent. In other words, this series here, we know for sure that it's going to be convergent in some interval of convergence here from -4 to 4, okay? So all values in between -4 to 4, we know that this particular series should converge, a power series should converge. And again, how do we know that? Well, we know that in general here, our power series should be of the form c sub n times x minus a raised to the n. So what we have going on here, it should say x minus a raised to the n. But again, since it just says x raised to the n, we know that this a here has to be 0. So everything is centered about 0. And if we're thinking that, and we know that at x equals 4, this is going to converge like this, then we know it's got to spread out the other way. And so our our radius of convergence is going to be from -4 to 4. And Here, let me go ahead and switch this. We know for sure that it's going to converge at -4. Not quite sure if it converges at 4, but we know it's going to be in this particular interval here, okay? So we know that much. So based upon that information here, then we should be able to basically figure out everything else that we need to know. So for this first series, let's come back here for a second. We notice that we just have C sub n, but note that we could think about this as C sub n times 1 raised to the n, okay? So in other words, if we plugged in a 1 right here and let 1 go to the n, we know 1 raised to the n, any single number is just going to be just 1, okay? So that is the same as this. So we know here x is equal to 1. So since 1 is inside of this interval of convergence here, we could say that this particular series is going to converge, okay? Now, by the same token, since 8 is outside of this particular interval of convergence here, we could say that this one diverges. And here we know that -3 is inside of this particular interval of convergence, so we can say that this one converges. So we'll say converge here, diverge here, converge here, okay? And then, of course, for this last one, we have 9 right here. The fact that we have this alternating part here, may or may not help us, but we know that because we have this 9 here, no matter what happens, it's outside of this interval of convergence here, so we know it's going to diverge as well. And so that's why here I have the series A is going to converge, because the series is essentially, the power series is essentially a power series when x is 1. The series for C is going to converge because 3 is inside of this particular interval, and B and D both diverge since 8 and 9 are outside of that interval, okay? All right, so that concludes the part 1 video for power series. Please tune in for part 2.